Boa noite a todos. Eu sou Carlos Quintela, diretor da FGV Energia. Agradeço a audiência de vocês nessa noite, tarde/noite, que hoje vamos falar sobre sistemas energéticos e as energias disruptivas futuras no mundo, com uma personalidade de tanto destaque que é o Dr. Amory Lovins. Mas antes disso, eu gostaria de apresentá-los. Eu gostaria de fazer uma colocação e apresentar o nosso principal patrocinador, a Shell do Brasil. Shell tem nos apoiado bastante com os eventos, é uma das parceiras da FGV Energia, e ela nos apoiou nessa jornada de 3 eventos internacionais que estamos fazendo. Nosso primeiro evento foi uns 10 dias atrás, foi a geopolítica contemporânea, e hoje vamos falar da energia disruptiva. E semana que vem vai ser a transição energética com o ministro Bento Albuquerque e a presença internacional também do diretor-geral da Agência Nacional de Energia, Dr. Fatih Birol. Queria agradecer muito a Shell, a parceria, em nome do Dr. André Araújo aqui presente, em nome do seu diretor Flávio Rodrigues, que tem nos apoiado bastante. E não poderia deixar de falar também a nossos apoiadores, que são nossos mantenedores da FGV Energia, que é o CEPEL, Furnas, PetroRio, Equinor, Eletronuclear, Norte Energia, Ipiranga e a Eni. Dr. Amory Lovins é cofundador e presidente emérito do Rock Mountain Institute, é também professor adjunto de Engenharia Civil e Ambiental e acadêmico da Universidade de Stanford. Ele foi consultor de energia dos principais governos e empresas por mais de 70 países. Para fazer a abertura do Amory Lovins, eu não poderia pensar em ninguém tão brilhante quanto ele. Então, eu gostaria de chamar o nosso presidente da Shell do Brasil, Dr. André Araújo, que a Shell tem despontado e saído na frente bastante das outras empresas com a parte de pensando no futuro e transição energética. Doutor André Araújo, por favor, as palavras são com você. Muito obrigado. Em seguida, passo a palavra para a Fernanda Delgado, que será nossa moderadora nesse evento. Obrigado, André Araújo, por favor.
Good evening. I will, Carlos, if you don't mind, just to host Mr. Amory Lovins, I will do my opening in English. I hope I am on the right translation mode here in our call. So good evening, everybody. I really would like to thank FGV Energia, particularly you, Carlos Quintela, and Fernanda, for the opportunity to be here and welcome Amory Lovins. And he is one of the early leaders on the discussions about energy transition. I know that the relationship with Shell is quite long, and Mr. Lovins has been acting and really generating a strong content about energy policies for probably more than 4 decades. And it's really safe to say that the energy transition topic, probably he was one of the ones that put in the map for reflection. Mr. Lovins' messages, they are very actual, probably more than ever. And for the work and some of the presentations that I have seen myself, there is always a touch on what makes sense to the market, always with support of science and technology. And he is a real a supporter of the role of the productive sector and the role of the organized society in the energy transition spectrum. I do believe that we are going through a time very special in the global economic scenario, probably more than ever for us in the energy sector. If we do remind probably exactly 1 year from now, within April and May, we had the lowest price in the oil. In reality, was a negative price, and at the same time, a major drop in the consumption of fuels. The situation clearly is not the same, but all this volatility and the perspective for lower prices put in doubt the speed of the transition, energetic speed for many people. But the reality is quite very different. In the last 12 months, we have observed, and particularly in Shell, we could see that with our customers, a major increase on the speed of the discussion on decarbonization, on the green recovery, and how we can really connect the economic development with a way to have a cleaner and efficient development. So within all these challenges that we are clearly going through, much more concern with the environmental debate. The question is not restrict more in the academy or government, is pretty much in the civil society that is much more connected with this discussion. And as we go through more and more with customers, we see most of them conscious and really with this ambitious to change their own choices. And so it's really a time for everybody to keep working together. Clearly, it's a time that we have to keep finding ways to make the economy growth, local scale, national, and global. We do believe that the growth in energy will be tremendous, but always the question is what kind of energy will be this one? And there are probably questions of billions of dollars, or probably, as Mr. Lovins would say, it's a question of $1 trillion. So we in Shell, we do believe that oil will still be needed for some time. And even though that in our strategy, it's very clear that we will be following the changes together with society. Mr. Lovins is always in some way challenging us that the moment of the peak oil is getting closer than most of us can imagine. And I think this is quite important to think about. So one of the questions is, how could we ourselves be prepared for that? So in a very some way, I do believe that the answer is diversification, and as well to be adapt to the local realities of every different location. We don't see that there is a single solution that will be able to address all the path to the energy transition. By example, if we look into the Brazilian case, for instance, should we keep accelerating the electrification of the Brazilian fleet, or we should find, or if there is a role of the Brazilian ethanol, and when I say ethanol here, I talk about second generation ethanol options for bioenergy, biogas. Another question in Brazil, it's very common on how long the pre-salt will keep attracting investments within these times of the transition, what will be the choices that the country will make regarding how competitive this can all be. And some of these choices may be not excluded, maybe just they can coexist. So new technologies will be quite revolutionary. And today, in the spirit of this debate, it's really a pleasure to have Mr. Lovins with us. The theme of his presentation about the disruptive futures of energy is an invitation for this type of reflection, out of the box, very creative. And with that, I really thank you, and I hope you enjoy the session today. So before giving the floor to Professor Lovins, I do believe, Fernanda, the ball is on yours. Not sure if I'm doing the right thing, but I believe this is the way it should go.
Obrigada, André. Thank you, André. Hello, everyone. Good afternoon. I'm Fernanda, professor and researcher of FGV Energia. It's a pleasure to be here with you today. Before I hand the floor to Dr. Lovins, there are some housekeeping for us here today. Everything we say today, me, Dr. Lovins, André, everything here regards our opinion and not FGV opinion, and that we send our image, we authorize FGV to use our image on this webinar. Everybody that follow us in the YouTube, please send us our questions. I will be delighted to make the questions to Dr. Lovins here. I will receive the question through the chat or through a little app there called Slido. Instead that, I would like to say you can choose the language that you want to hear us here at Zoom. Before pass the word to Dr. Lovins, I would like to mention the 3 last books that Dr. Lovins published, and The Smallest Profitable, The Hidden Economics and Benefits of Making Electrical Resources the Right Size from 2002, Winning the Oil Endgame from 2004, The Essential Amory Lovins from 2011, Reinventing Fire. This is my favorite one. This is my favorite one. This is the Portuguese version. I have this one, Dr. Lovins, from 2011. These are the last publications, the book publications for Dr. Lovins. And I guess André told everything about Dr. Lovins, the vast and the enormous publications that he has. And I always say that there is no single solution for energy transition, and there is no one-size-fits-all solutions, especially for underdeveloped worlds. Instead, so I handle the floor to Dr. Lovins. Please, Dr. Lovins. You're on mute.
Boa noite. Obrigado. Let me see if I can make this work. We were having some difficulty before with the setup.
You're doing fine.
Okay. Muito bem.
Muito bem.
Thank you for the honor of reporting some energy and electricity surprises that I hope may help you in Brazil. I'm going to take General Eisenhower's wise advice to make tough problems soluble by expanding their boundaries to encompass more options and more synergies, so they include everything the solution.
Dr. Lovins, you are not sharing your screen.
Well,
let's try again.
This happens.
Always happens.
Take your time.
There we go.
It's okay now.
Play.
So that when you move the boundaries of the problem out, then it can include everything the solution requires. All 4 energy using sectors, transport, buildings, industry, and electricity, can save more energy faster together than separately. All 4 kinds of innovation, not just technology, but also design, not only public policy, but also business strategy, can combine to create deeply disruptive game changers while the old industries are still putting on their boots. Henry Ford's auto industry, Thomas Edison's electricity industry, and John D. Rockefeller's oil industry changed the world. If Ford and Edison took a very long nap on one of their car camping holidays together and woke up and saw their businesses today, they would recognize almost everything except the electronics. Yet their industries now face vast disruptions as 21st century technology and speed collide head-on with 20th and even 19th century institutions and rules and cultures. And now the first two of these three great industries, automobiles and electricity, are coming together to eat the third one, hydrocarbons. As we might imagine, Ford mischievously muttering to Edison, let's see what happens when electricity displaces gasoline. Then those electric cars add flexibility and cheap distributed storage and make batteries cheap for all, helping the grid to integrate variable solar and wind power so distributed renewables replace giant thermal power stations and their fossil fuels. Let's start, as we always should, with efficient use. Saved energy is already the world's biggest energy source. Just the energy saved worldwide since 1990, about 2/3 by smarter technologies, now supports more energy services than oil does. If the total primary energy demand of the United States, for example, had kept growing in lockstep with GDP since 1975, Americans would have used this much energy, but instead they cut that use by more than half, saving cumulative energy equivalent to 25 years of current use. Meanwhile, renewable energy output doubled, but with 28 times less cumulative impact than the savings. Renewables get nearly all the headlines because they're visible, but energy is invisible, and the energy you don't use is almost unimaginable. Yet, from 2010 to 16, the world's saved energy avoided 3 times as much CO2 as all the renewable and nuclear growth. Another bit of history. Around 1975, United States government and industry all said that primary energy productivity, the GDP produced per unit of primary energy used, could never go up. A year later, I heretically suggested it could rise 257% in the next 50 years. So far, it's risen 154% in 44 years. But just the innovations already added by 2010 can raise energy productivity by another threefold, twice what I originally thought, and at 1/3 the real cost. Today, that looks conservative because optimizing buildings, vehicles, and factories as whole systems, not as piles of parts, can often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns. This paper, free online with a fun 4-minute video abstract, you can just search on the title, How Big is the Energy Efficiency Resource, explains why making energy savings several-fold bigger can actually cost less, because it uses not more but fewer devices, and not fancier but simpler devices, more artfully chosen, combined, timed, and sequenced. Metal ore bodies and oil reservoirs are finite and depletable assemblages of atoms, but energy efficiency resources are infinitely expandable assemblages of ideas, depleting only stupidity, a very abundant resource. A few examples. My wife, Judy, and I live, the building you see a little behind me, 2,200 meters above sea level in the Rocky Mountains near Aspen, Colorado, where temperatures used to dip to -44 Celsius. We've seen 39 days of continuous midwinter cloud. It was snowing last week. We expect frost tonight. But our house does no combustion. That's so 20th century. Super insulation, ventilation, heat recovery, and big super windows insulating like 16 or even 22 sheets of glass, but looking like 2, costing less than 3, make this building 99% passive solar heated, 1% active solar. Super efficiency added less construction cost than eliminating the heating system subtracted. So we saved 99% of space heating and water heating energy, 90% of household electricity, and half the water, all with a 10-month payback in 1983. Today's technologies are better and cheaper. The central atrium behind me, seen in this picture in a February snowstorm, has so far produced 78 passive solar banana crops. Number 78 is just at the left end of the picture of me here. Our house helped to inspire several 100,000 European passive buildings that likewise have no heating and roughly normal construction cost. Wherever you live, integrative design gives many benefits from each expenditure. The white arch just behind and above me, or in the top of the upper middle photograph, has 12 different functions, but it has only one cost. And it works out anywhere. Soon after we moved in here, the architect from Thailand, Professor Sunthorn Bunyatakarn, visited this house and decided to adopt its integrative design approach and adapt it for his own 350 meter square meter house he was building in Bangkok. And of course, it's the opposite climate. It's hot and wet. He saved 84% of the air conditioning capacity, 90% of the air conditioning energy, with exactly normal construction cost and better comfort. And almost everyone in the world, or in Brazil, lives in a climate somewhere between his and mine. We used integrative design in 2010 to retrofit the Empire State Building, saving 38% of its energy, later 43%, with a 3-year payback. 3 years later, our cost-effective Denver retrofit saved 70%, making this half-century-old government building more efficient than what was then the best new US office. That in turn is only 1/3 as efficient as RMI's passive, net positive, no mechanicals innovation center 10 minutes from here. Now, a building in southern Germany is using 2/5 less energy than ours. And yet all these technologies existed more than a decade ago. What has mainly improved is not technology so much as design. How did our retrofit save 2/5 of the Empire State Building's energy? Remanufacturing its 6,514 windows on site in a temporary window factory set up on a vacant floor into super windows that pass light through but block heat, plus better lights, office equipment, air handling, and so on, cut the maximum cooling load by 1/3. Then renovating smaller chillers instead of adding bigger chillers saved $17 million of capital cost, paying for most of the improvements and cutting the payback to 3 years, or less than 1 year if we had counted non-energy benefits to the owner or the tenants. A big energy service company using disintegrated design had offered the same 3-year payback with only 1/6 the savings we got. They lost the bid. Now the owner is going back with even better integrative design to save another 40+%. 11 days ago, our India-based Global Cooling Prize announced the winners of a contest to cut affordable window air conditioners' climate impact by at least 5-fold. Both winners raised energy efficiency more than 5-fold. But better buildings can first displace that cooling equipment. These mid-rise apartments, proven popular in Mumbai's monsoon, use passive, convectively vented double walls and super efficient ceiling fans to keep you feeling 16 to 19 Celsius degrees cooler at just 2% higher construction cost. With a few further refinements, they could deliver decent comfort with no air conditioning. In muggy India, Rohan Parikh's team built 1.5 million square meters of offices using 80% less energy than normal, with 10 or 20% lower construction cost, but superior comfort and satisfaction. Glare-free lighting is delivered throughout by contract. If workers complain of glare and demand blinds, then the architect doesn't get paid. You might look at this building on the left and say, is that upside down? Well, yes, the builder or the designer turned it upside down because the shading saves more cooling equipment cost than you pay extra for the structure to support that upside down design. Daylighting is an art as much as a science, but its technology can be arrestingly simple. This primary school in Curitiba, in Paraná, had a roof overhang too shallow to stop glare on the windows. Now, in the nearer room of this photograph, the glare was so strong that inside you can't see with the lights off because there's too much light in the wrong place. But adding a shade outside the other window and then continuing it on the inside as a light shelf that bounces light up and back along the ceiling lets you see very well, still with the lights off, and save 3/4 of the electricity, which pays for the textbooks. Students also learn 20 to 26% faster in well-daylit classrooms. So those cheap sheets of white painted wood or cloth or plastic to distribute the daylight properly are important to national democracy and development. Whatever exists is possible. IPCC reported 7 years ago that among European new buildings on the left and retrofitted buildings on the right, with bigger savings towards the right in both cases, the better projects saved up to at least 90% of their energy without costing more per unit of saved energy. So you can see all these points that are very close to the horizontal axis at very low cost in new buildings and in fixing up old buildings. Now, there are many projects that cost much more by not adopting the best practices shown. The difference is the business opportunity. And about a decade after those buildings, new techniques are emerging. For example, purely radiative cooling can keep people comfortable outdoors in humid Singapore at 32 degrees or more without moving, drying, or cooling the air. Instead, in a shaded but open-ended 10 square meter pavilion like a bus stop shelter, this experiment cooled people just by absorbing far infrared radiation from their bodies into vertical panels cooled by surface tubes circulating slightly cooled water. To prevent heating by and condensation from the air, the front of the panel is shielded by an air-gapped 50 micron polyethylene film that lets through 82% of the infrared that your body radiates. As the extended psychrometric chart shows, circulating water around 23 to 25 degrees can deliver comfort up to at least 32 degrees at 80% relative humidity. The mild cooling you need for that water can often be done passively with no electricity by special surfaces that radiate infrared into the sky and therefore feel cool to the touch, even under the noonday sun. What about home appliances? This Swiss fist-sized heat pump can deliver 6 to 15 units of hot water per unit of electricity. Now, contrasted with the 6 to 15 times less efficient chuveiro elétrico that costs you perhaps 20 reais, but it costs Eletrobras and the rest of the power system 1,800 to 3,000 reais in capacity to power it. That's an easy way to bankrupt the power sector. On the right is a dramatically more efficient, safe, and otherwise superior Swiss electric cooking system using vacuum insulated pots with 2.5 to 4 or more times less electricity than induction cooktops, and much less than natural gas. All such things, of course, should be made in Brazil and bought whenever they are cheaper than supplying more electricity. The highest leverage for fair global development comes from efficiency gains to make electricity affordable to the poor. In this 27-watt electric household, Berkeley Lab uses solar panels 1/3 smaller than shown in the picture to power 7,000 looks of LED lights, a mobile phone charger, a clock radio, a table fan, and a 56-centimeter color television. Their super high efficiencies cuts the total capital cost in half. So you can empower twice as many off-grid families with the same money and also enable cheap and very reliable DC microgrids. Now, from a macroeconomic perspective, if you invest to make things that save electricity rather than make more, you will need roughly 1,000 times less capital and you'll recover it 10 times faster. So lower intensity and faster velocity multiply. You need about 10,000 times less capital for the most capital intensive sector, electricity, which devours about 1/4 of global development capital. Freeing up that capital to fund other development needs is the biggest macroeconomic lever we know for development. Just buy negawatts whenever they are cheaper than megawatts and reward providers for cutting your bill, not for selling you more energy. What about industry, which uses half the world's energy and electricity, mainly to make stuff? But smarter structural design can profitably save at least half of the world's cement and steel that now release 15% of global CO2. For example, substituting tension for compression structures in this stadium and bridge typically gives better strength, aesthetics, and cost with 1/8 the tons. Fabric forms can save over half the concrete in many shapes by putting strength and stiffness only when they're needed. And then those weight savings compound because you need less strength to hold up less weight. This 4 or 5 centimeter thick folded concrete slab replaces, like corrugated cardboard, a 30 centimeter thick steel and concrete normal slab. It can also help you fit 3 stories with unchanged ceiling height into the vertical space normally needed by 2. An airy 3D printed bridge can replace massive concrete structures that mostly support their own weight. This beautiful stainless steel bridge was 3D printed in Holland. And then producing the remaining cement, steel using green hydrogen, and other materials can adopt not just cleaner, but also super efficient processes and equipment. For example, RMI's latest 50+ billion US dollars worth of industrial redesigns typically found 30 to 60% energy savings on retrofit, paying back in a few years across a big range of sectors and far outperforming the brown zone on the upper left, where most energy service companies deliver disintegrated design. Our new build industrial projects generally found 40 to 90+% savings with lower than normal capital cost. Factory costs less to build. Let me give an example that applies to both buildings and industry. Just better pipe and duct design, saving about 80 or 90+% of friction, therefore a pump power and fan power, could, if fully deployed, save roughly half the world's coal-fired electricity, or 1/5 of all the world's electricity, with payback times typically less than a year in retrofit and instant in new build. But this isn't yet in any standard industrial textbook, government study, industry forecast, or climate model. Why not? Because it's not a technology. It's a design method. And few people yet think of design as a scaling vector, a way to make things big fast. But it could spread perhaps even at the speed of Twitter, because you can convey it with a picture. To wring out friction, we simply use big pipes and small pumps, not small pipes and big pumps. So the blue pump on the right here looks so small, you think someone slipped a decimal point, but it's correct for pipes that are that fat, because friction drops as almost the 5th power of diameter. And notice the pump is raised up to meet the pipe rather than lowering the pipe to the floor to meet the pump and then back up again with more bends and more friction. To eliminate those elbows and their friction, we lay out the pipes first, then the equipment. So these 10 chillers, normally in a neat row with a lot of right angle bends in the pipes, have been staggered and spread out to make those bends go away. We lay out the supply pipes as if they were drains. So our colleague Peter Rumsey's retrofit of a California museum's condenser water pumping loop with a wide joint, fat pipes, a very shallow curve, and a pipe running diagonally through the air. This cut the pumping energy by 3/4, paying back in 2 or 3 months, and it eliminated 15 pumps that will never again waste energy and maintenance costs. I like mega pumps. Then he repiped the chilled water loop and added variable frequency drive to double the flow and save 85% of the energy. In big buildings, normally we pipe cooling tower water back to the chiller's condenser like this. But if we lay it out this way instead, everything gets better. Why don't we always do this? Force of habit. We should bend minds, not pipes. What does such savings mean for the 3/5 of global electricity that's used in motors, half to run pumps and fans? Well, in a typical pumping system, from the fuel burnt in a thermal power plant to the end use, so many successive losses compound that only 1/10 of the energy in the fuel comes out the pipe as flow. But now turn those compounding losses around backwards from right to left, they become compounding savings, and every unit of flow or friction you save in the pipe saves 10 units of fuel cost, emissions, and global weirding at the power station. And as you go back upstream, the components get smaller and cheaper, so the total capital cost goes down. Then we can make the motor systems 80 or 90% smaller and at least twice as efficient by a whole system retrofit, using not just the usual 2 improvements, but 35, of which 28 are free byproducts of the first 7. Then you save several fold more motor energy at about 1/5 the unit cost of the normal partial retrofit. 4 years ago, electricity was only 1/5 of the world's final energy, but making it used 65% of global coal, 40% of gas. It emitted 42% of fossil CO2, 48% of sulfur oxides. It took 49% of energy investment. It was 39% of consumers' energy bills. So saving electricity has many big kinds of leverage. 18 of 30 members of the International Energy Agency, member nations, shrank their use of electricity from 2010 to 17. More efficient use cut those 30 nations' electricity demand growth by more than 4/5, from 1.6 to 0.3% a year. But how much more could be saved? Well, even with very limited integrative design as a conservatism, US electricity use could shrink by 1/4 by 2050, despite all electric automobiles and a 2.6-fold bigger GDP. This means the efficiency of using electricity would get 4 times better. The average cost of doing that would be 1/10 what we pay to buy each kilowatt hour today at retail. So that vast overhang of unbought efficiency holds at risk many investments in power plants and fuel and grids. What about oil? Well, nearly half of US oil fuels automobiles. It's the biggest oil use in the world. So let's start with their physics. Just 1/5 of a modern US car's fuel energy reaches the wheels and moves the car. The rest is lost first. Of the tractive load moving the car, nearly half, rising as the cube of speed, heats the air that the car pushes aside. Most of the rest heats the tires or the road, and only about the last 6% of the fuel energy accelerates the car and then heats the brakes when you stop. But it gets worse. 19/20ths of the mass you are accelerating is not you, it's the heavy steel car. So just 1/20th of that 6%, or about 0.3% of the fuel energy ultimately moves the driver. Not very gratifying after 1 1/3 centuries of devoted engineering effort. Both acceleration and rolling resistance of the tires depend on mass. So mass causes most of the tractive load. Now, automakers cut losses mainly in the orange part, the powertrain, because that's where most of the losses are. We had a famous bank robber in America, Willie Sutton. Someone asked him, why do you rob banks? He said, because that's where the money is. Well, it's much harder to reduce powertrain losses than reduce tractive load because so much has already been done. And it's much less rewarding because saving 1 unit of energy in the powertrain, the propulsion system, saves only 1 unit of fuel in the tank. But saving 1 unit of energy at the wheels avoids 4 or 5 additional units lost in getting that energy to the wheels. So it leverages 5 or 6 units of fuel saved in the tank. Therefore, we should first reduce tractive load, then improve the powertrain. The powertrain gets smaller for the same acceleration. That saves more mass, and it also saves capital cost to help pay for the lightweighting. Just like the efficiency of my house shrank and indeed eliminated the heating system enough to pay upfront for the efficiency. Let me give an example. Whole system design can make automobiles several-fold more efficient, making electrification faster and cheaper. So this carbon fiber electric car that I drive was made of a material that everyone said was too expensive for volume production of cars, much more per kilogram than steel. But we don't buy cars by the kilogram, we buy them by the car. So let's look at what happened. How is it that this quadrupled efficiency car was profitable from the first unit? And now we've sold over 150,000 from BMW. It's one of the top 10 electric vehicles in Europe still. Well, how did they do this? The carbon fiber was paid for by needing fewer batteries to go the same distance with less weight, and then fewer batteries recharge faster. Integrative design makes the saved weight compound or multiply much faster than other automakers assume. The assembly is radically frugal. Making this car needs 2/3 less capital and water, half as much energy and space and time as making ordinary cars from metal. The conventional body and paint shops, the hardest, costliest steps in making the car, are eliminated. Much better for the workers. No compromise, 1.9 liters equivalent per 100 kilometers, many, many driver benefits like half normal turn radius, very useful in cities, excellent crash safety. Oh, but this isn't the end of the matter. 2 hypercars plan to enter the US market, indeed the world market, late this year, both from firms I advise to disclose that, are going to change the game again. Most drivers will not need to recharge this 2-seat electric 3-wheel vehicle because the solar cells, 3 square meters on top, capture enough energy to drive 40 to 60 kilometers every day. It's as if your present car parked in the sun each day will magically add 7 liters of fuel to its tank. If you want to make a long road trip, you can quickly recharge the batteries with household electricities for ranges up to 1,600 kilometers. Now, outside here, I have electric cars, very good ones from BMW and Tesla. They're among the most efficient sold, but this 2-seat carbon fiber car will nearly triple their efficiency to the equivalent of less than 0.7 liter per 100 kilometer. And that composite body looks very crashworthy. Then there's a Dutch firm called Lightyear with a 5-seat 4-wheel electric car, 725 kilometers range, light, aerodynamic, 5 square meters of solar cells, 0.9 liters equivalent per 100 kilometers, and it can add 12 kilometers of range for every hour it's parked in the sun. So by making these very efficient, in fact, the one on the left has less air drag than the windshield wipers or the side mirrors on a standard American pickup truck. That level of efficiency means that the charging infrastructure others must pay for, these vehicles aim to bypass. The same design principles apply to heavy vehicles. My team helped Walmart's fleet of heavy lorries, the world's biggest civilian fleet, to save half its fuel per case in a decade. That includes smarter logistics, but just better technology can profitably make these heavy trucks at least 3 times more efficient, as one maker expects to prove this year. Airplane efficiency, too, can rise 3 to 5-fold, like these decade-old designs in the bottom row by Boeing, NASA, MIT. But the revolution accelerates. Tesla's battery electric truck, due out this year, more than triples efficiency with 40% sleeker aerodynamics, lightweighting that offsets the battery weight, and a 2-year payback. Or revealed last August, here's a flight-tested air taxi that could fly nonstop from Sao Paulo to New York at the speed of a small business jet, with 1/6 its operating cost, 1/8 its fuel use. That's before electrification. A bigger version already designed could hold well over 20 passengers and looks set to blow up aviation's business models. More leapfrogs are emerging. 2 years ago, MIT and NASA selected or tested this strong, tough 4 1/3 meter long structure that is 98.3% lighter than a typical aircraft wing. Every part of its shape passively morphs in real time like a bird's wing to match the real-time flight conditions for best efficiency. Thousands of such identical cells molded from engineering plastics, or there are 10 to 100 times stronger alternatives, can be robotically assembled into an airplane of any desired shape. That opens revolutionary prospects for lightweighting, aerodynamics, lower cost. It's been prototyped as a car for Toyota, as an airplane for Airbus, and it could even make a vacuum balloon needing no helium, crushworth but buoyant enough in the atmosphere to lift 24 times the payload of a jumbo jet. So add all this up, and I think you conclude that the oil and gas reserves unsellable for competitive reasons look bigger than the reserves unburnable for climate reasons, putting oil owners even more at risk from market competition than from climate regulation. The cost of getting automobiles completely off oil has fallen from $18 per say barrel 10 years ago to less than $7 today, heading below zero in the next few years. So oil became uncompetitive even at low prices before it became unavailable even at high prices. Now, with electricity, as with fuels, technology and design are both moving efficiency into fast forward. Prior lighting improvements, for example, are being swept away as LEDs in each decade get 30 times more efficient, 20 times brighter, 10 times cheaper. What else changes this fast? The rest of the energy transformation, modern renewables. LEDs backwards are PVs, photovoltaics. So solar and in aqua wind power costs have plunged below the dashed lines. The cost of fossil fuels fed into US thermal power stations, and that has often made old coal and gas and nuclear plants uneconomic just to run, even if building them were free. The electricity revolution, though, is bigger. It includes shifting from molecules and atoms to bits and packets, from hardware to software, from hierarchies to networks. Electricity is changing from centralized, supply-focused, fossil and uranium-fueled and brittle to distributed, customer-focused, renewable, and resilient. The information age informs, enables, and organizes customers to take power into their own hands. Maybe that's the biggest change. You know, it's wise to sell customers what they want before someone else does. And customers are figuring out they can buy far fewer electrons, use them more productively and timely, produce their own, even trade them with each other. For example, Dutch customers can buy homemade electricity directly from other customers on this peer-to-peer website of Van de Bron, literally from the source. My friend bought his electricity from the guy in the upper left picture because the price is right, and it's a really cute piglet. And then he got a long handwritten Christmas card from his electricity supplier. What big utility can dream of such customer intimacy? Indeed, powerful disruptions are converging on the electricity industry from at least 8 directions. These 8 Pac-Men of the apocalypse move fast. They don't just add, they exponentiate. They're not lone wolves, they hunt in packs, they multiply quickly, and they can gobble up half of utility revenues in this decade. Together, they're creating an alien competitive landscape faster than most utility cultures can cope. 7 years ago, all central power plants were called dinosaurs. And the full quote is, too big, too inflexible, not even relevant for backup power in the long run. Who said that? It wasn't Greenpeace. It was Union Bank of Switzerland. And now a new wave of Pac-Men is coming over the hill with more behind them. Renewables in 2020 were about 82% of the world's total net additions of generating capacity. And the International Energy Agency predicts that'll be about 95% through 2025 because, says Bloomberg, last year, renewables became the cheapest bulk power source in 90% of the world, and soon in all. So US wholesale electricity prices, for example, this aqua range, now widely exceed the average contract prices of wind power in blue, solar power in orange. Those are temporarily subsidized, but less than non-renewables are. Now, in unsubsidized world markets, renewables at or below $30 a megawatt hour, the diamonds at the lower right, keep falling through $20, including in Brazil. Last month in Saudi Arabia, they hit $10, about a decade earlier than most people expected. Modern batteries included in the filled-in squares are already cheaper than gas peakers. Bloomberg finds that variable renewables plus backup, which can be renewable, non-renewable, storage, or demand side, are now the cheapest way to meet a steady load. So they have dethroned the so-called baseload thermal plants that no longer have a business case. Now, the Paris Agreement's 1.5-degree aspirational goal would require stopping 80% of the coal plants that ran in 2010 by 2030. You'd have to close one a day to 2040. You'd have to close almost all by 2050. But renewables' new market prices make this profitable without counting any value for mitigation. So how to retire early is a nearly year-old study from RMI and partners, examining 95% of the global coal fleet and finding that using efficiently structured financial instruments, you could close and replace all coal plants now with modern renewables, including battery storage, be cost neutral in 2 years. And by 2025, you'd be saving over $100 billion a year. This is especially true in China and India, the middle row in this graph. So this is a very good business deal. Gas comes next. New and old combined cycle power plants no longer have a business case, even with the cheap-looking fracked American gas. Their market is collapsing because all of their outputs, energy, and capacity and ramping and flexibility and ancillary services like voltage and frequency stability, these can all be provided faster, better, and cheaper by locally customized, carbon-free, clean energy portfolios that combine a locally optimal mix of demand-side and renewable and storage assets. This substitution could strand more than $100 billion of planned US gas plants and $500 billion of gas supply to fuel them. Investors quickly took note. Now, modern renewables also scale up in a fundamentally different way. Traditionally, we built these giant cathedral-like thermal power stations, each costing billions of dollars, taking many years to license and build. But now instead, each year, a similar total amount of investment can, year by year, build a factory that produces each year thereafter enough solar cells to generate each year thereafter as much electricity as your cathedral will ultimately make. In other words, each little solar panel on the right matches the output of the big power plant on the left, and therefore solar power worldwide is scaling faster than cell phones. And yet we're still told that only coal, gas, and nuclear stations, or in Brazil also hydro if there isn't a drought, can keep the lights on because they're 24/7, while wind power and solar are variable and thus supposedly unreliable. But variable does not mean unpredictable. Here is how accurately the French grid operator in a stormy winter month forecast a day ahead the actual output of the country's wind farms. I'll bet they wish they could forecast demand that accurately. Well, now, a decade later, wind operators in East Denmark are bidding wind power into the day-ahead hourly auctions, just like thermal capacity, because today's wind forecasting is so accurate that the operators are more confident they can deliver on their contract tomorrow than the grid operators are confident that when they push the start button, their peaker will actually start. Indeed, we built the grid because no generator is 24/7. They all break. And when a giant thermal plant fails, you lose 1 billion watts in milliseconds, often abruptly, often for weeks or months. So grids were built to manage this intermittence by backing up failed plants with working plants. And in exactly the same way, but often at lower cost, grids can manage the forecastable variations of solar and of wind power by backing up those variable renewables with a portfolio of other renewables, all forecasted, integrated, and diversified by type and by location. Let's see how these moving parts fit together in a difficult case, the state of Texas, whose grid has no big hydro dams. It's only 1% interconnected to neighboring states. In 2050, an expected summer week of load shape could look like this, or it could get much smaller and less peaky with profitably efficient use. Then we can make 86% of the annual electricity with wind and with solar cells. You see how peaky they are. And you can make another 14% from dispatchable renewables, small hydro, geothermal, burning feedlot biogas in combustion turbines, burning agricultural or municipal or industrial wastes, burning obsolete energy studies. That's my favorite. Anyway, you now have 100% renewable supply. It turns out every hour of the year, but it doesn't well match the load, the dashed line. So to make the match, you can put the surplus electricity into two kinds of distributed storage that are worth buying anyway: ice storage air conditioning and smart charging of electric cars. Then you can recover that energy when needed and fill the last gaps with unobtrusively flexible demand. Then you have 100% renewable electricity every hour of the year with no bulk storage, no big hydro dams, only 5% left over to make hydrogen or ammonia. So the economics should be excellent even at today's prices, let alone the lower future prices. Now, some grid operators already do such choreography today to far exceed last year's renewable fraction of 38% in Europe and about 31% in the world. Germany and Britain, for example, are half renewably powered. Denmark expects to be 86% renewable this year, Scotland 100%, they almost made it last year. And already these and some other European countries with modest or no hydropower, in contrast to Brazil's 2/3 hydropower generation, are meeting half to 3/4 or more of their electricity needs from renewables right now. So the former East German ultra-reliable grid company, 50 Hertz, was 60% wind and solar powered 2 years ago. They target 100% renewables reliably integrated by 2032. So as my colleague Clay Stranger says, the operators have learned to run these grids the way a conductor leads a symphony orchestra. No instrument plays all the time, but the ensemble together continuously makes beautiful music. Now, for normal grid balancing, we have not just one method, bulk storage in magenta, but about 9 carbon-free ways to make the grid flexible, reliable, and renewable. I've sketched them here in order of increasing cost. It's a conceptual chart. Your actual costs will vary. We're now calculating the actual numbers. But the point is that bulk storage comes last, not first. So we need not wait for a storage miracle, though some are emerging, and the market isn't waiting, especially in countries without Brazil's fast regulatable hydropower. Now let's look more closely, just for illustration, at the second box from the left, demand response, which means using electricity more timely. RMI did an hourly simulation, again for the Texas power pool, ERCOT, looking at summer 2050, where the gross load from non-renewables is in green, but the net load after you subtract the renewables from the big solar peak in the middle of the day, then has this very rapid ramp called the duck curve that goes up in the late afternoon as the sun goes down, but people get home and turn stuff on. So we looked at 8 kinds of demand response that engage electric vehicles, home plug loads, residential and commercial domestic hot water, and heating and cooling controls. And together, these 8 can conveniently cut in half the summer daily load range, save 1/4 of the non-renewable capacity, make renewable energy 1/3 more valuable, and pay back in about 5 months. Now let's look a little more at the electric vehicle part, because those sales are soaring as battery costs plummet. And of course, the two each drive the other. In the next few years, electric cars will cost no more to buy than gasoline cars. And good electric vehicles are much nicer and cheaper to drive. Their abundant cheap batteries imply distributed solar power everywhere, gas industry distress, the end of thermal power stations, vast distributed storage and demand flexibility, and perhaps much of the grid's becoming a stranded asset like phone company copper. This prospect gives utility executives nightmares and venture capitalists sweet dreams. Ubiquitous electric vehicles mean an immense storage and ancillary services resource that is now parked about 96% of the time. Already today, you can drive your charged up battery car to a football game in Amsterdam's Green Stadium. You can plug it in to help run the stadium, leaving ample electricity to get home with, and they let you watch the game for free. The integrator, based in Zurich, is called the Mobility House, and it supplements those incoming cars with 148 stationary Nissan Leaf battery packs, 42 of them percent of them reincarnated in a second life. They all provide valuable services to the grid. So the firm is building a 100 megawatt portfolio of stationary storage in Germany, Holland, and France. Here's the first 30 megawatts, all using battery packs that are in the electric car business, but not in cars that are currently driving. Maybe the car was crashed. Maybe it's a spare part sitting in a warehouse. In 2018, this integrator installed the first electric car that was licensed as a power station on the German grid. It can get paid for providing frequency stabilization services. Of 21 services that stationary or mobile batteries can provide, the Mobility House is already commercially active in 10 and is launching 3 more. Meanwhile, efficient and electric autos are morphing from pigs, that is, personal internal combustion, gasoline, steel-dominated vehicles, to SEALs, shareable electronic autonomous lightweight service vehicles. Those 2 changes in technology and 3 changes in business model are all simultaneous, mutually reinforcing, vigorously in play, and sped by smart policies and strong commercial ambitions in India and in China. We're very active in both of those. Meanwhile, the rules are changing. In 2010, almost half the world's new cars were sold in China. Only 5% of people owned one, and yet this 100-kilometer traffic jam took 12 days to unsnarl. Building roads causes traffic, so politicians are starting to realize this and to change the rules to ensure that drivers get what they pay for, but pay for what they get. Non-automotive mobility is improving too. Bus rapid transit, invented by my friend Jaime Lerner and his team in Curitiba, transformed the Hangzhou street on the left to the street on the right, while carrying 800,000 riders a day. It can achieve subway route density at about 5% the cost of a subway. And now in nearly 200 cities, it's carrying over 30 million commuters a day. China also has over 200 million electric bicycles. Shenzhen has 100% electric buses and taxis, over 70,000 electric delivery vehicles, soon 100%. A city of 13 million people with more electric buses than the top 5 United States urban bus systems have total buses. And urban design is also changing. China plans in the next 15 years to build new cities for as many people as America has. And so far, China has designed cities around cars with an arterial vehicle network, 13-lane super highways between, but integrating and distributing where people live, work, shop, play, pray, means that people don't need to travel far or by car. Adopting instead a capillary web designed around feet means 2/3 less driving, 1/3 less concrete. It builds a human ecology with vibrant commerce, rich social life, equal or better throughput, cleaner air, happier citizens. It's the story of Rua de Flores in Curitiba. And the 53 cities already doing this, and more to come, will not use much oil. So assembling all these opportunities, our business and design book, Reinventando o Fogo, rigorously showed how to triple US energy efficiency and quintuple renewables by 2050, needing no oil, no coal, no nuclear energy, at least 1/3 less natural gas, while saving $5 trillion net present value, growing the economy 2.6-fold, strengthening national security, and cutting fossil carbon emissions by 82 to 86%. But we found this would need no new inventions, just 2010 technology, no acts of Congress, but with smart city and state policies could be led by business for profit. How are we doing so far? Well, the first 9 years of this 40-year journey are pretty well on track, green actual versus blue proposed, I think largely because the private sector smells the $5 trillion on the table. That's exactly what should be happening. These best buys are also the most effective solutions to big global problems that hazard every country's security and prosperity. And if you like any of these outcomes of reinventing fire, you can support this transition without having to like every outcome and without having to agree about which outcome is most important. Focusing on outcomes, not motives, can turn gridlock and conflict into a unifying solution to our common energy challenge. Stimulated by those US findings at the G20 5 years ago, China's National Development and Reform Commission published its roadmap for China's energy revolution. It details how China can save over $3 trillion US, run a 7 times bigger economy in 2050 than 2010, but use today's energy 7 times more productively. Emit 42% less carbon, burn 80% less coal, get 13 times more GDP from each ton of fossil carbon. This roadmap strongly informed the 13th 5-year plan, whose energy authors were our steering committee. That strategy continues so firmly in the 14th plan that China doubled its renewable installations last year alone, adding more wind power in 2020 than the whole world had added the year before. Now, extrapolating those on-track US and adopted Chinese and similar European findings to the other half of the world could achieve the minimal Paris Agreement ambition, a 2-degree climate target, about 18 trillion US cheaper. Then reinvesting some of that in natural systems carbon removal could get us to the aspirational and necessary 1.5 degrees, with trillions of dollars left over and huge progress on the Sustainable Development Goals. Making climate protection not costly but profitable should also simplify the politics. You know, climate science models have conservatively understated the speed and the runaway potential of climate change. Climate policy models conservatively understated what we can do to stop climate change. Offsetting these two biases, what Jeremy Grantham calls the race of our lives is very much on. Despair and complacency are equally unwarranted. Global CO2 emissions were flat in 3 of the 5 years, 2015 through 19, as energy savings and carbon-free supply growth averaged roughly the pace we must sustain for 2 degrees, or half the pace we need for 1.5 degrees. So now we must accelerate. And a powerful tool, which I'll end with, is capital market dynamics. Incumbent energy suppliers, feeling the obvious competitive threats, understandably focus on the need for price to exceed cost. But many forget the other part of the business condition. Value must exceed price. If competitors offer a superior value proposition and run off with your revenues, it doesn't matter if you can profitably sell what your former customers are no longer buying. These energy transformations can flip markets with breathtaking speed. On Manhattan's Fifth Avenue, in 1900, in these old photos dug up by Venezuelan Stanford innovator Tony Seba, 1900, you have to look hard for the first car. Anyone see it? There it is. 13 years later, you have to look even harder for the last horse. The horse and buggy industry thought it would have many decades to adapt, but Henry Ford's Model T car got 62% cheaper in 13 years to 1921. Car-owning households soared from 8% to about 60% in a decade to 1928. 3/4 were financed by a General Motors and DuPont innovation called car loans. Today, our solar modules just got 80% cheaper in 5 years. Our batteries got 89% cheaper in 10 years. 3/4 of our rooftop solar is innovatively financed. Ford's and Edison's industries are merging to eat Rockefeller's industry. Thus, the pace of transformation is set not by incumbents, but by insurgents, who are not inhibited by incumbents' business models or legacy assets or cultures. You know, the horse and buggy thinking is dangerous, but still common. The late ex-oilman Maurice Strong said, not all the fossils are in the fuel, but the ex-chairman of DuPont, Edgar Willard, reminds us that firms hampered by old thinking, he said, won't be a problem because they simply won't be around long term. You see, investors flee before customers do. because capital markets keenly sniff out disruption. Once they think you're in or even headed for the toaster, they don't wait for the toast to get done before they decapitalize you and invest in your successors. Already, trillions of dollars have prudently fled the fossil fuel industries as they hemorrhage capital and talent and political influence. The world's top 16 listed hydrocarbon companies combined were recently worth less than Apple. Carbon Tracker investment analyst Kingsmill Bond explains this brutal logic of the capital markets. He says any fast-growing challenger will rapidly take all the growth in a slow-growing market. As a rule of thumb, incumbent sales will peak when the challenger gets to about 3% market share, as in these examples. So this is because most investors don't just want size, they want growth. So they try to sell their shares just before sales peak, because then stagnation strands assets and competition drops prices. That's why the coal industry has lost 3/4 of its market value globally, 99% in the US. But now this collapsing value is spreading to oil and coming next for gas. What's happened already? Well, peak nuclear power output, peak coal, peak automobile sales, peak fossil fuel generation have already happened. Fueled autos are now in their 4th year of shrinking sales because electric cars took more than all the growth. Last year, global plug-in auto sales soared 43% through the pandemic, while total auto sales fell 14%. The IEA says last year's pandemic slump undid the last 4 years of the world's energy growth and the last 9 years of its CO2 growth, while renewables grew 45% faster. So by the time demand recovers, if it does, renewables will probably have expanded enough to supply any future growth, tipping fossil fuels into permanent decline. Many respected forecasters are now starting to show this. And therefore, peak oil, peak fossil fuels, peak CO2 emissions probably all happened in 2019. Now, Brazil has made important contributions to that revolution on the supply side, but I think its immense potential on the demand side remains largely untapped. One last thought. This global energy transformation is not just fundamental, it is elemental. The first industrial revolution was the age of carbon, creating our prosperity and the world's mightiest industries from coal and oil and gas. But now that obsolete age of carbon is giving way to the modern age of silicon. Silicon microchips, telecommunications, and software turn people from isolated to networked, systems from dumb to smart, grids from analog to digital, and potentially from dirigiste to democratized. Silicon power electronics make electricity interconvertible and precisely applicable, replacing fiery molecules with obedient electrons. And silicon solar cells enable the ascent of energy from mining the fires of hell to harvesting the breath and radiance of heaven. So our responsibility and our opportunity is to help enable the new energy system, not protect the old, to build back better, to move fast to fix things. So the global energy transformation can move at the pace and the cost of design and of software, not of infrastructure, and can be not constrained by the inertia of incumbents, but sped by the ambition of insurgents, including, I dare say, many of you. Muito obrigado pelo seu bom trabalho e pela sua atenção.
Thank you, Dr. Lovins. Was really a great lecture. I would have a lot of things to comment. Design, from pigs to seal, the Pac-Man from Apocalypse. I really like that thing. But let's go to the Q&A section. I would like to start with a question from my dear friend, Professor Horta Nogueira. He's saying, "Dear Professor Lovins, Thank you for sharing your clarifying reflections with us. We learned a lot from your previous works. As you know, in some sense, Brazil has already started its energy transition, promoting intense participation of bioenergy in transport and hydropower for electricity generation. Could we believe that we represent an example to be replicated towards a soft and brave new world of energy? Or should the developing countries follow the global trend of the rest of the world on wind and solar?
Well, Brazil is competitively installing a good deal of wind and solar, and it's making its way in the market very nicely. We watch this with admiration. We like the prices. Brazil has, of course, this extraordinary sugar ethanol program, which I think actually I learned from Jose Gelderberg, my old friend. The most important thing may have been making all the cars accept any sort of fuel, gasoline, ethanol, or anything in between, because this imposed strong price discipline on the market, and it was a very good idea. Now, I think opinions differ about all the long run implications of the ethanol, and it may also have some trouble competing in the long run with about a 5 to 10 times more productive plant. This may surprise you because we all learned in school sugarcane is the most productive plant. It's not. It's actually behind me, the Indonesian sugar palm, Arenga pinnata. And that has 55 other forms of value as well used in Indonesia. It grows all over the tropics. So if you want biofuel, there may be even better ways to do it. And that's a much more diverse ecosystem because this tree actually doesn't grow well in monoculture. It likes to have many diverse friends around it. The hydro, as you have learned, as Chile learned also, is very prone to drought, and diversification is called for. I think the main missing element is to add much more strength to all the long-standing but not yet sufficiently vigorous efficiency efforts. And I think this takes two basic policies. One is always compete or compare efficiency and indeed demand response with supply, buy the cheapest one, and then make sure the providers are rewarded not for selling you more energy, but for cutting your bill. That is, decouple their profits from their sales volume, but let them keep a little part of whatever they save you by helping you be more efficient or by saving money in their own operations. And then you and they will have completely aligned incentives, not opposite incentives. That's a very powerful way to run a business. We've done this reform now in 18, I think, of the United States for electricity, 26 for natural gas. The electric and gas trade associations support it. And I think it's a good idea in almost anywhere. Of course, the way people run their grids and regulate and so on differs all over, but this principle of rewarding the best buys first can be adapted, I think, to any society.
Thank you. From your lecture, you say like climate protection is something very profitable, and will eliminate the oil industry, and can have the power to make the economy profitable again, like we are on a recession situation right now all over the world. This goes very much with Mr. Biden, your new president, is doing right now, bringing to America this new plan for energy transition with $2 trillion in investments. How do you see this new plan of the new government in the United States for energy transition?
Well, it's what's happening in the market anyway. It's interesting that despite Mr. Trump's efforts to restore the coal industry, actually coal-fired power plants were retired faster after he left were retired faster under his administration than the previous one, and now faster still. The hydrocarbon industry is in economic distress as well, not just because of fluctuations in world price, but because the fundamentals are not so sound. I've had the pleasure of working with Shell for 48 years now, and indeed we're working now with them on the next bit of strategy, and it's a very challenging business. I hope that industry's great skills can be adapted to the requirements of the new system, but it's not easy. It's not obvious that they can do a lot of small things rather than just a few big things, that they can work as well on the demand as on the supply side. And of course, there are some big things that need doing. For example, the industry skills are great for offshore wind, but not all the skills are adaptable. It's early to tell how the politics of energy will play out in the United States, where the fossil fuel industry owns one of the major parties and can block most actions in the upper house. But there are a lot of other ways to get things done. The economy is not the government. The government is not the federal government. We have 50-odd state governments. We have local governments. Most of the action in energy in the United States is not at a federal level. We have rather a weak federal system. Rather, it's state, local, and civil society, and especially the private sector, which is very much going in the direction I described.
Great. My friend Fabiola Sena just wrote me saying that we have to add another D for the energy transition. We have to say this decentralization, decarbonization, digitalization, and now design.
And democratization.
Andrea, would you like to ask something or to add something?
I would add democratization, which is actually a very important driver of the Energiewende in Germany, which, by the way, has gone quite well, despite a disinformation campaign to try to make people believe the opposite. Yes. But, if you read German and if you read the statistics, you'll find they've done remarkably well in a lot of ways. Thank you, whoever that was, for adding design. And I think that's a very important missing element that I hope Michelle and others on the supply side will pay more attention to. I think it's a great business opportunity for everybody, including the suppliers. Actually, we've done 7 design projects with Shell over the years, trying to spread this around the company. And it's not easy to see exactly how to spread it, but I know Brazilian engineers and architects are uncommonly clever and original. I think you have a wonderful opportunity to make Brazil a leader in this area. I'm teaching now extreme energy efficiency, so-called, at Stanford, the art and science of integrative design. And I hope we can figure out ways to spread this around Brazil as well.
Andrea, would you like to add something?
Yeah, a few comments. I think we are getting to the closure. So, Mr. Lovins, first of all, thank you very much. Always challenging thoughts, but you presented in a very, let's say, easy way to go through your thoughts. And first of all, I was impressed to see banana crop in Colorado. That was amazing to see, but really very impactful. Your messages on design, on integrated design, and also in structural design. It's probably good to see how we can move to the design investment and pretty much early stage instead of doing amendments as we go. If we can have this structured design, that probably will help a lot in the energy efficiency. And I think it was really a great message that you deliver on the importance of energy efficiency. That is a major pillar on our strategy, and you demonstrate that there is such a long opportunity ahead of us on this space before just creating too many things. I was very impressed to see the design cars that you showed, and just to make a kind of a joke, but we have Brazilian mechanical engineers in a Shell event called Eco Marathon, and the designing are getting very close to the ones that you presented here. So pretty much amazing the way that you share the importance of trying to see beyond the unknowns and having your mindset that things will change, even though that we will not know exactly the path. The trends are demonstrating that technology will come and complete the gap that eventually many people have in their mind, and we should expect the changes coming very fast. And my final comment is great to see the way that you're looking to distributed energy instead of centralized, and how that can be much more easy, particularly in a developing world where you don't need to go through the same, it's easy now to say same mistakes, but the same structure that the energy industry has been developed in the past. So thank you very much for your comments, for your presentation, and very glad to meet you virtually. Thank you very much. And thank you, Fernanda. Back to you.
My pleasure. Well, this is the end of our webinar. I'll pass the word to you, Dr. Lovins, for your final considerations for your Brazilian audience.
Well, I hope you all stay safe in these difficult times and use the extraordinary depth of talent, ambition, and entrepreneurship in your society to do a uniquely Brazilian version of what I described, and help lead all of us in a much better direction. Thank you.
Well, in my name, in FGV Energia name, in my director, Carlos Quintela, I really appreciate your time, Dr. Lovins, your kindness to be here with us for more than an hour and a half. André, thank you so much for joining us today, for your speech today. Everybody who has been watching us until right now, thank you so much for joining us today, and see you on Wednesday 13. Gente, muito obrigada por ter assistido a gente até agora. Vejo vocês dia 13 no nosso próximo webinar aqui da FGV Energia, com a grande final do Prêmio Projeto Caro. Gente, boa noite. Obrigada por ter ficado com a gente até agora.
Obrigado.
And thanks to the interpreters.